The Greek philosopher Democritus imagined matter was composed of discrete, uncuttable pieces, atoms, in the 5th century BC. But it took until the 19th century before scientists found convincing evidence of his atomic hypothesis. However, in the early 20th century, Ernest Rutherford and his researchers at the Cavendish lab showed that these atoms could indeed be split. Rutherford instead proposed a new set of 3 basic building blocks: protons, neutrons, and electrons. In the century since then, we have learned things are not so simple. Protons and neutrons are themselves composed of smaller particles, called up quarks and down quarks. There are 4 other flavors of quarks in addition to these 2, forming 3 generations of increasing mass. Likewise, there are 3 generations of electrons and light neutral particles called neutrinos, which collectively are called leptons. These 12 particles collectively are called fermions and make up all the matter in the known universe. There is also a group of 5 bosons, which are responsible for the forces and masses experienced by the other particles. Photon exchanges create the electric forces between charged particles. Gluon exchanges create the strong nuclear force that binds quarks together. W and Z boson exchanges create the weak nuclear force that allows particles to change their flavor, and the Higgs boson interacts with other particles to increase their mass. So in total, we have 17 fundamental building blocks in what's called the Standard Model of physics. But wait a second. It turns out that 9 of these particles are so heavy as to be extremely unstable. Due to Einstein's mass-energy equivalence, the heaviest particles are able to unleash their high mass energy by decaying into other particles with smaller mass and high kinetic energy. They do so very quickly. A few millionths of a second after any of these particles is created, only the 8 types shown here will remain standing. Except under Big Bang-like conditions, the quarks and gluons are confined to only exist inside larger particles, which are classified as hadrons. Of the hadrons, only the proton and neutron have a lifetime longer than a microsecond. The neutrinos? Well, they barely interact with matter at all. So for the purposes of material science, you can safely ignore particle physics after 1932, when the known particles were the proton, neutron, electron, and photon. But just for today, let's dive into the details of what Robert Oppenheimer called the Subatomic Zoo, and discover how we learned what the world is really made of at its most fundamental level. Welcome to Atomic Universe. I'm Dan Bergstrom, material scientist. If you saw the last episode, you may remember how Carl Anderson discovered the muon when he moved his cloud chamber to Pikes Peak to study particles in cosmic ray showers. This particle presented quite a puzzle to particle theorists since its mass was neither as light as an electron nor heavy as a proton. Anderson initially called it a mesotron, the prefix coming from the Greek word for intermediate, mesos. At first, this particle was thought to be the one that had been hypothesized in 1934 by Japanese theorist Hideki Yukawa, who was trying to explain the force that held protons and neutrons together in the nucleus. This force had to be quite strong to overcome the electrostatic repulsion of all those positively charged protons. But despite its strength, the strong attraction had to be a very short-range force because any protons outside the nucleus only experience repulsive forces. Yukawa knew the electromagnetic force was carried by photons, whose zero mass allowed this force to travel long distances at the speed of light. Yukawa hypothesized that the strong force was carried by massive particles with short lifetimes, explaining their short range. He named these particles pions. To estimate their mass, he noted that the isotopes of boron and carbon, which differed by 1 proton, had a mass difference that was slightly less than 1 atomic unit. Since mass and energy are equivalent, Yukawa reasoned that the missing mass represented the binding energy of the added proton to the other nucleons, and thus the mass of the particle responsible for this force must be on the same order of the missing mass. A particle whose mass was a fraction of the mass of a proton, like the one Anderson discovered on Pikes Peak, could be a major confirmation of Yukawa's theory. But it turned out that particle wasn't the right one. As carriers of the strong nuclear force, negative pions should be absorbed relatively easily into the nuclei of any matter they pass through. Careful measurement of the absorption rate into blocks of carbon in 1947 showed that Anderson's particles were not as strongly absorbed as expected. And in May of that year, a new, slightly heavier particle was discovered by physicists from the University of Bristol studying cosmic rays in the Pyrenees Mountains. This new particle was eventually confirmed to be the predicted pion, and Anderson's particle was retroactively named the muon. Cosmic ray studies continued to find new particles over the next several years and were designated with letters. The kaon was discovered in 1947, the lambda in 1950, and the chi in 1952. Following Anderson's Greek nomenclature, particles lighter than the proton were called mesons, and particles heavier than the proton were called baryons, from the Greek word for heavy, baris. But despite the success of cosmic ray studies, artificial means of creating high-energy particles were soon to take over the limelight of particle research. After World War II underscored the importance of nuclear science to national defense, national laboratories in both the States and Europe funded massive particle accelerators capable of reaching greater and greater energy. Prior to the war, Ernest Lawrence's Berkeley Radiation Lab had started construction on a massive machine designed to accelerate particles to an energy of 200 million electron volts, a cyclotron featuring a 184-inch, 3,700-ton magnet. This machine was repurposed during the war to be a testbed for the technology used to separate uranium isotopes for the Manhattan Project. But by 1946, it was up and running again as a particle accelerator, and was upgraded from the original cyclotron design to a machine called a synchrocyclotron. As discussed in the last episode, cyclotrons were based on the principle that charged particles orbiting in a magnetic field do so with an orbital frequency given by the magnetic field divided by 2 pi times the ratio of the particle charge to mass. In a constant magnetic field, electric pulses tuned to match that orbital frequency can repeatedly accelerate particles to very high energy with relatively low accelerating voltages. This trick only works, however, if the mass of the particles remains constant. At 200 million electron volts, particles are starting to reach relativistic speeds, which causes the particle's mass to increase according to Einstein's theory of relativity. So to reach top energy, this cyclotron needed to decrease the oscillator frequency in sync with the shifting orbital frequency. This synchronization made this machine a synchrocyclotron. This synchro prefix was also used to name the next breakthrough accelerator design for reaching higher energies, the synchrotron. Proposed independently by Ukrainian Vladimir Veskler and Berkeley physicist Edward Macmillan in 1944, the idea of the synchrotron was to keep particles orbiting at a fixed radius by increasing the magnetic field in sync with the speed of the particles as they accelerated. This design proved to be much more scalable than the cyclotron, eliminating the need for magnetic fields or vacuum to be maintained in the interior of the ring. In the synchrotron design, particles orbit inside an evacuated ring with electromagnets placed at the bends in the tube to steer them around. This design allows the bends to be separated from the straight segments in a racetrack configuration. These straight sections can then more easily incorporate other accelerator elements, like one or more high-frequency RF accelerators, injectors for introducing pre-accelerated particles, strong focusing magnets to improve beam intensity, and of course, particle detectors. The first attempt to build a large-scale synchrotron was undertaken by Mark Oliphant. Oliphant had improved the Cockcroft-Walton linear accelerators at Rutherford's Cavendish lab, but was now running his own lab at the University of Birmingham in England. Spec'd to exceed 1 billion electron volts, a giga-eV, the synchrotron started construction soon after the war, but it suffered from technical difficulties and underfunding such that it didn't begin operation until 1953. By then, it was already obsolete. A synchrotron twice as big had come online the year before, at Brookhaven Lab on Long Island, and was dubbed the Cosmotron. The Cosmotron could accelerate protons through its 236-foot-long racetrack to reach an energy of 3.3 GeV. By 1954, Berkeley had an even bigger one named the Bevatron, a 400-foot-long circuit that could reach 6.2 GeV. By 1956, these new American accelerators had chalked up many new particle discoveries: the sigma baryon, the antiproton, the antineutron, and the delta baryon. It was also discovered that most of these particles had variants with positive, negative, and neutral charges. The delta baryon even had a variant with a double positive charge, twice that of the proton. Each particle's intrinsic angular momentum, or spin, was determined through the measurements of the magnetic strength. In units of the reduced Planck's constant h-bar, the baryons either had 1/2 or 3/2 spin, placing them in the category of matter particles like the proton and neutron. Mesons had 0 spin, which was expected for force-carrying particles like the photon and the pion. The muon, however, had 1/2 spin, so it was reclassified from a medium-weight meson to be a lightweight particle like an electron in what was called the lepton family, after the Greek word leptos, meaning small and thin. An even lighter particle than the electron was proposed by Wolfgang Pauli back in 1930 to explain the energy that seemed to go missing during radioactive beta decay. This proposed particle was named the neutrino by Enrico Fermi after the Italian word for little neutral one, but it proved elusive to find until 1956, when the neutrino was finally discovered by Los Alamos physicists Frederick Reines and Clyde Cowan, who placed their 10-ton detector next to an intense source of beta radiation. after considering using an atomic bomb as a radiation source, they settled for the nuclear reactor at the Savannah Power Plant in South Carolina to make their discovery. Altogether, there were several dozen known particles by the mid-50s, most of which had not been predicted by the theorists. Willis Lamb famously captured physicists' frustration with the Subatomic Zoo by noting that while the finder of a new elementary particle used to be rewarded by receiving a Nobel Prize, one should now be punished by a $10,000 fine. So what to make of these particles that no one ordered? Well, one thing they had in common was that they were not stable. To first order, the speed with which a particle decays increases with the mass energy released during the decay event. Muons decay into electrons in a couple of microseconds. Charged pion and kaon particle lifetimes are similar and on the order of nanoseconds. When these particles decay, they will most often create a muon or antimuon so as to conserve charge, as well as a neutrino which carries away excess energy. But things are very different when you compare the neutral pion with the neutral kaon. The neutral pion, which decays into massless photons, has a lifetime about 1 billion times shorter than the charged pion. Because charge needs to be conserved and all charge-carrying particles are massive, charged pion decays can't release as much mass energy, so they take longer. Strangely, however, the more massive neutral kaon lifetime is much longer than the neutral pion. Half of kaons last about 90 picoseconds before decaying into pions, and half of them last a much longer 5 nanoseconds before decaying into pions and leptons. The neutral lambda baryons are similarly strange, with lifetimes lasting about 1/4 of a nanosecond. Chi and sigma baryons are a mix, with some very short-lived particles and some strangely longer. But notably, those with very short lifetimes decay into particles that themselves have strangely long lifetimes. Some sort of strangeness is conserved in quick particle decays, which can only dissipate after a long decay time. To describe this behavior theoretically, physicist Abraham Pais and Murry Gell-Mann formalized strangeness in 1953 as a quantifiable property inherent to particles. The relative strangeness of a particle could be determined because the total strangeness was conserved during the creation and fast, strongly decaying events, just like charge and spin. The weak, slower decay modes did not conserve strangeness, so strangeness itself could dissipate, but those decay events took longer. After quantifying each particle's strangeness, Gell-Mann realized in 1961 that laying out all the particles against coordinates of spin, charge, and strangeness created octets of the particles, which he called the Eightfold Way, joking that it was like the Eightfold Path of Buddhist philosophy. The discovery of the Eta meson later that year helped build confidence in this model by completing the spin-zero octet. The pleasing symmetry of this pattern was highly suggestive of some underlying order, and in 1964, Gell-Mann and George Zweig independently proposed models that explain these particles as being made up of smaller pieces, which Gell-Mann called quarks. By assuming 3 different quark particles, up, down, and strange, as well as their antiparticle equivalents, one could build all the particles in the Eightfold Way in a way that accounted for their mass, charge, and particle lifetimes. To see how this works, let's start with the spin 1/2 baryons. If you imagine the octet as the corners of a flattened cube, moving along the y-axis increases the charge by 1, moving around the x-axis increases the magnitude of the strangeness, and moving along the flattened z-axis changes both. Let's make the assumption that each particle is made of 3 quarks, and that adjacent particles differ by only 1 quark so that by swapping one out for another, it converts to the neighboring particle. For example, to move from the neutron at 0 strangeness and 0 charge to the proton above it on the y-axis, let's replace one of the 3 quarks, let's call it a down quark, with another, let's call it an up quark. This implies that the up quark needs a charge which is 1 greater than the down charge, but has the same strangeness. Similarly, for all the other pairs of particles with the same strangeness, replacing a down quark with an up quark will result in particles with charges increased by 1. By the same argument, we can move along the x-axis by replacing the down quark with a quark that has the same charge but increased strangeness. Let's call that the strange quark. And finally, we can move along the flattened z-axis by replacing a strange quark with an up quark to reduce the strangeness while increasing the charge. By mapping these moves onto all the baryons, then, we can show in a straightforward way how they are made of these quark triplets. But something very odd emerges when you do the math to figure out the individual quark charges. Take a look at the proton whose charge is +1. It's composed of 2 up quark charges and 1 down quark charge. But the difference between the up and down quark charges must be 1. If you add these two equations together and divide through by 3, you find that the charge of the up quark must be plus 2/3. Since the down quark charge is 1 less, it must be negative 1/3. And the strange charge is the same as the down. This result was something of a problem for quark theory, since no experiment had ever seen a particle with fractional charge before. One thing that quark theory did explain well was the mass of the particles. The magnitude of the strangeness could be mapped fairly well to the masses of the particles. This implied that while the up and down quarks were similar in mass, the strange quark must be substantially heavier. Finally, the total spin of the particles being 1/2 means that if the spin of each quark is also 1/2, one of the 3 quarks in any triplet must have opposite spin from the other 2. Spin alignment explains why the neutral lambda and sigma baryons have different masses even though they both consist of 1 up, 1 down, and 1 strange quark. In a neutral sigma particle, both the up and down quarks spin in opposition to the heavier strange quark, resulting in a higher energy state than in the lambda particle where the up and down quarks have opposite spins. Since energy is equivalent to mass, the neutral sigma is heavier than the lambda. Now let's turn our attention to the zero-spin mesons. Due to their lighter mass, it makes sense to model mesons as only having 2 quarks per particle with canceling spins. To obtain both positive and negative charges, we must use the antiquarks as well as the quarks. So again, let's move up the y-axis, replacing a down quark with an up quark to increase charge. But now we will say we can move down the y-axis by replacing an anti-down quark with an anti-up quark. Similarly, moving along the x-axis is replacing a down quark with a strange quark in one direction, or replacing an anti-down quark with an anti-strange quark in the other direction. And in the flattened z-axis, we have the exchange of a strange quark for an up quark, or their antiparticles. Bringing these together brings us the Quark model of the mesons. Again, at the center of the diagram, we have 2 particles. Neutral pions can be either up anti-up pairs or down anti-down pairs, and in fact, neutral pions will actually oscillate between these 2 configurations whose masses are similar. The heavier neutral eta meson includes the possibility of a strange anti-strange combination. In the late 60s then, physicists had a model which used simple building blocks of quarks to explain the charges, spins, and lifetimes of most of the particles in the subatomic zoo. In this model, particles with strange quarks are unstable, as are any particles containing antiquarks. That meant only 2 particles were stable enough to be the building blocks for long-lasting atoms, the proton with 2 up quarks and 1 down, and the neutron with 1 up and 2 down. In addition to this quark theory, Gell-Mann predicted a massless particle responsible for the strong force which binds the quarks together, which he called the gluon. Since the gluon is massless like the photon, the range of the strong force can be very large, but it differs from the electromagnetic force in that its strength increases with distance instead of decreasing. This explains why the odd fractional charges of the quarks are never seen outside of other particles. The strong force confines the quarks to always be grouped with other quarks, except under Big Bang-like conditions of intense energy. To see how this strong force works, consider trying to remove a d quark from a neutron. As it pulls away, the energy pulling it back gets so large that the gluon will be able to snap by decaying into other particles. In the case shown here, an up and anti-up quark pair are generated. The up quark is then pulled back, turning the neutron into a proton, and a negative pion is formed from the down and anti-up quarks. Now, if we imagine this taking place inside an atomic nucleus, this negative pion will attract a nearby proton and combine with it. With this combination, the anti-up quark will annihilate one of the up quarks existing in the proton, and the d quark will remain, transforming it into a neutron. This sort of particle creation, annihilation, and transformation is what really binds the nucleus together, and it is in fact the real mechanism behind Yukawa's theory of pions as carriers of the strong force. By 1968, the details of a theory of the weak force had also been worked out by a trio of theorists, Sheldon Glashow, Steven Weinberg, and Abdus Salam. This theory predicted that weak particle decays were mediated by charged W or neutral Z bosons, whose large masses explained why some decays were relatively slow, like those involving the strange quark and beta decay. Beta decay, which is a particularly slow decay mode, occurs when a negative W boson allows one of the neutron's down quarks to decay into an up quark, an electron, and an antineutrino. This newly created up quark stays inside what was the neutron, turning it into a proton. This theory also explained how the weak force is closely related to electromagnetism, forming a unified electro-weak theory of particle interactions. As a corollary to this unified field theory, Peter Higgs had proposed another, even more massive boson to explain how the other particles acquired their masses. This is now called the Higgs boson. So the Quark model was consistent with the observed properties of particles, but was it true? There was a clear prediction from the Quark model which came from looking at the particles with 3 halves spin. These particles are inherently unstable, since aligning the 3 quarks in the same spin state to add up to 3 halves is like trying to align 3 magnets to have their north and south poles aligned. Since like poles repel, spin 3 halves particles will rapidly decay to spin 1 half by flipping one of the quarks to an anti-parallel spin. In this lowest energy state, it's impossible for 2 quarks of the same flavor to have the same spin state due to the Pauli exclusion principle, the details of which we'll have to wait for another time. But while all 3 spins are aligned, the extra energy gives these particles the extra degree of freedom they need to have 3 quarks of the same flavor in the same particle. That means that the odd +2 charge delta baryon can be explained as being composed of 3 up quarks. Likewise, 3 down quarks in combination create the negative delta, a particle with 0 strangeness and -1 charge, existing with 3 halves spin, but without a 1/2 spin counterpart. Physicists at the time also realized this model implies there should be a particle composed of 3 strange quarks. Extrapolating from the other particles, they predicted the existence of a triply strange, negatively charged particle with a mass of about 1.65 GeV, heavier than any of the particles yet known. This be-all and end-all baryon was called the omega, and once the search for it began, it was quickly found in 1964 by the Cosmotron at Brookhaven. Further validation of the Quark model came from a series of experiments at Stanford, which were completed in the early 1970s. The Stanford Linear Accelerator, or SLAC, is built like a synchrotron unrolled into a straight line, essentially a 2-mile-long drag strip for accelerating electrons up to 50 GeV. Researchers at SLAC use these electrons to probe the interior of protons in much the same way that Rutherford's gold foil experiment had used alpha particles to probe the insides of atoms. And they saw similar results. Just as Rutherford had shown that alpha particles scattering at high angles indicated something hard and small inside the atom, SLAC researchers saw high-angle electron scattering was too high for a particle as big as the proton. There must be something small and hard inside it. Although these pieces were initially referred to as partons, subsequent experiments confirmed the properties of these particles matched those expected from Gell-Mann's quarks. In particular, the odd fractional charges of the quarks were confirmed by modeling neutrino scattering intensities in experiments conducted in 1975 at CERN, the European Center for Nuclear Research, near Geneva, Switzerland. These results led to the general acceptance of the Quark model throughout the physics community. As the theorists in the 1960s and 70s began to get a better handle on the subatomic world, the experimentalists continued building bigger and more energetic synchrotrons. In 1960, a half-mile-long ring, called the alternating gradient synchrotron, was powered on back at Brookhaven. The AGS pushed protons to 33 GeV and used alternating horizontal and vertical magnetic fields to achieve stronger focusing than previous synchrotrons. In the 1970s, the largest U.S. synchrotron ring was built in Batavia, Illinois, at a facility later named Fermilab. It was 3.9 miles long and reached 400 GeV. In the 90s, this ring would be doubled up to become the Tevatron, enabling 980 GeV protons to collide with antiprotons moving in the opposite direction, for a total collision energy of 1.96 tera electron volts. At the same time, over in Europe, CERN was keeping pace with the completion of a proton synchrotron in 1959, which was over 600 meters long and could reach 26 GeV, followed by the super proton synchrotron in 1976, which was similar in size to Fermilab. There was also a synchrotron exclusively for accelerating electrons located in Hamburg, Germany, called DESI, which is short for the Deutsche Elektronensynchrotron. It became operational in 1964 and could accelerate electrons to 7.4 GeV. In 1962, Leon Lederman, Melvin Schwartz, and Jack Steinberger used the AGS at Brookhaven to discover the muon neutrino, validating earlier predictions that 2 electron flavors should be matched by 2 neutrino flavors. In quark theory, however, there were 2 flavors of -1/3 charge quarks, but only 1 quark with a +2/3 charge. This led theorists in 1964 to predict a 4th quark, called the charm, to give 2 full generations to all the fermions. A charmed meson was in fact co-discovered by 2 teams in 1974, a Brookhaven group led by Samuel Ting, who named it the J meson, and a SLAC group led by Burton Richter, who called it the Psi meson. Despite being unable to decide on the name, the J-psi particle did add substantial credibility to the Quark model within the physics community and led more theorists to work on making new predictions. By 1975, those theorists predicted a third generation of quarks and leptons, filling out the full list of particles that we know today as the Standard Model. Now it only remained for the experimentalists to actually find them. The first particle found in the third generation was in the electron family, called the tau, and it was discovered at SLAC in 1975 by a group led by Martin Pearl. Fermilab researchers found the rest of the third generation, the bottom quark in 1977, the top quark in 1995, and the tau neutrino in 2000. Meanwhile, the Europeans were able to confirm the field gauge theories for the strong and weak force by discovering gluons in 1979 at DESY and finding the W and Z bosons at CERN in 1983. As the 20th century came to a close, that left only the Higgs boson yet to be discovered. But this was a big deal. Not finding any Higgs boson would be a big blow for the Standard Model, which would otherwise have been wildly successful. In the early 90s, $4.4 billion was budgeted for the construction of a 50-mile-long superconducting super collider in Waxahachie, Texas, designed to find the Higgs. But this ambitious project had its funding cut in the third year of construction, when its estimated cost ballooned to $8.4 billion. And so, the hunt for the Higgs was left to the Europeans. Construction of the more modest 17-mile-long Large Hadron Collider at CERN started in 1998 with a budget of 7.5 billion euros, and it was completed 10 years later. Using its smaller synchrotrons as boosters, the LHC pushed protons up to 6.8 tera electron volts. Since the mass of the Higgs boson was not precisely known, it seemed likely this new synchrotron would be powerful enough to do the job, but it was far from certain. Years went by without clear data in favor of the Higgs' existence. But finally, in 2012, combining results from two different teams at CERN, the discovery of the Higgs was proven and announced to the world, a resounding triumph for the theorists and their Standard Model of physics. Thus ends the story of how we know what things are made of. But before we end today, the last thing I want to show you is what those theorists think the insides of protons and neutrons actually look like, with a couple of cartoons. In addition to their electrical charge, quarks have what are called color charges, named after the primary colors of red, blue, and green. These charges are carried between the quarks by gluons to create the strong force, binding quarks together. Unlike the binary electrical charges of positive and negative, it takes all three color charges together to make a neutral white particle. This cartoon, made by the folks at CERN, is showing those color charges as if they were real colors, which they aren't, and it shows the gluon fields as curled up vibrations of color. As mentioned before, this gluon field creates a force that increases as the quarks move apart, effectively confining the quarks to only exist within larger particles. An alternate depiction of the proton shown here was made by the folks at MIT. This model shows how the quarks actually exchange their color with one another through the gluons. The simulation also shows that looking at the proton with a faster shutter speed reveals a boiling plasma of quarks and gluons moving around inside the proton at near the speed of light. The neutron is built similarly, and the strong force reaches between the neighboring particles in the nucleus to bind them together and form atomic nuclei. And as we have seen in previous videos, the positive nuclei attract electron clouds that complete the atoms and determine the chemical nature of the elements. And so here we conclude this series of videos on the making of matter. Now that we have completed this deep dive into atoms and their building blocks, the next series will start to look at exactly how these atoms join together to make all the materials in the world around us. Thanks for watching.